All right, so picking up where we left off last class, we had this function 2x cubed minus 3x squared minus 36x plus 14. And we wanted to find the relative extremas of the function. So, rewriting everything, we've got f of x is equal to 2x cubed minus 3x squared minus 36x plus 14. Since we want to find the relative extremas, we're going to want to find whenever our derivative is equal to 0, right? So we're going to want to take the derivative here. Taking the derivative, we find that f prime of x is equal to 6x squared minus 6x minus 36. So we can factor out a 6 here. To get x squared minus x minus 6. And now we can factor this polynomial out to get 6x minus 3 times x plus 2. Agreed? So from here, since what we're trying to find is the relative extremas, we want to set this thing equal to 0. Primed of x is equal to 0. This is going to tell us that x is either equal to 3 or to negative 2. Right? So now we've got our critical numbers. We're going to break it up, our interval from negative infinity to infinity, up into 3 other smaller intervals. X is equal to negative 2, x is equal to 3. This first interval is going to be x less than negative 2. The second interval is going to be x between negative 2 and 3. And this third interval is going to be 3 is less than x. Now, we're going to try to find a test point in each of these intervals. Since we've got x is less than negative 2, let's choose 3. Since we've got 0 in this interval, let's go ahead and choose that. And since 4 is in this interval, let's go ahead and choose that. Now, our derivative at 3, my mistake, negative 3, typo. Our derivative at negative 3 is going to be negative 6 times negative 1. The It's going to give us 6, right? Times 6 is going to be 36. So x is going to be greater than 0, right? At 0, we have 6 times negative 3 times 2. That's obviously going to be negative, right? And at 4, we're going to have 1 and 6. So this is obviously going to be positive. So from this, we can tell that we're going to be increasing on this interval, decreasing on this interval, and increasing on this interval. So if we go from up to down, the negative 2 must be a relative max, right? And if we go from down to up, x must be a min, right? Now looking at what we've got, compared to the answer, we found that in our interval, we were in fact increasing, decreasing, increasing, right? And comparing it to the graph, negative 2 is in fact a max. 3 is in fact a min, which jives with what we found, right? Folks at home, what do y'all think of this? Is it making sense?
Yeah, it's a little difficult, but it makes sense.
Cool. So what's really happening here? Let's take a moment to actually think about this whole thing. What we're doing is we're approximately finding the behavior of our function using the derivative. That's 2. This is 3 over here. We're saying the derivative tells us something about the slope, right? So if the slope is positive, our function must be increasing. If the slope is negative, it must be decreasing. And if it's positive again, it must be increasing. So from this, we get that our function is going to look something like this, right? Can y'all see that graph that I just drew? People at home, can you see the graph that I just drew?
Yeah.
Cool. looking at this, we can see then kind of that correlation, right? And this is further over. Like that. We can kind of see how this is going to behave then, right? Our min is here, our max is up here. And the reason why this occurs is because we know that our function is continuous, so we're never going to lift up our pit. So if we're going from increasing to decreasing, we've got to be going up, 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 down, 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 implying there's a max. Going from decreasing to increasing, we've got to be going down, 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 up, 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 implying there's a min. And using this sort of logic, this is how we're going to be able to determine whether our critical numbers are mins or our maxes or our mins. Yeah? Having said that, let's consider x to the fourth minus x to the third. X to the fourth minus x to the third. Our derivative then is going to be f prime of x is equal to 4x to the third minus 3x squared well, the first thing we can do is try to factor out that x squared, right? Now we want to factor out the 4 and the 3 somehow, right? Or we can just go ahead and leave it in this form. I would suggest leaving it in this form. This is going to tell us that our derivative is equal to 0 whenever x is equal to 0 or one over 4 is going to cancel out this 4, right? So if we choose 3 over 4, we're going to have 3 minus 3, right? So 3 over 4 must be our other 0. All right, now with this, let's go ahead and draw out our table. We've got x is equal to 0, x is equal to 3 over 4. This is going to be the interval x less than 0. This is going to be the interval x between 0 and 3 over 4. And this is going to be the interval x greater than 3 over 4. Let's choose a test point of -1 here. Let's choose 1/2 here. And let's choose 1 here. Choosing those values, when we throw in -1 here, -1 squared is 1. 4 times -1 is going to be -4. So this thing is going to become -7 times 1. So our derivative at -1 is less than 0. Plugging in 1/2, x squared, when x is equal to 1/2, it's going to come out to be 1 over 4. So that's going to be positive. 4 times 1/2 is going to be 2, minus the 3 is going to be -1. So this whole thing is going to come out to be less than 0. Now plugging in 1 squared is going to be 1. 4 times 1 is going to be 4. Minus 3, it's going to give us -1, right? I mean, it's going to give us 1. So our derivative at 1 is greater than 0. So in this interval, we must be decreasing, decreasing, increasing. Does everybody agree with that? So what we've got here, looking at the graph, is that 0 is this point here, right? What we're doing is we're decreasing, 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 kind of flattening out for a little bit. Decreasing, decreasing, decreasing. Now we're going to increase.
There's no relative max on this one.
Right, there's no relative max, exactly. Only a relative min. So x is equal to 0, just a point. It's just a flat point in our graph. But x equal to 3 over 4, it's going to be a min because we're going from decreasing to increasing, right? In other words, the critical number doesn't necessarily always provide us with a min or a max, right? It just provides us with a spot where our function flattened out for a second.
So if you're going increasing to decreasing, would you have a max then?
Yes.
Okay.
Yeah. If we go from increasing to decreasing, we're going to have a max. But if we go from decreasing to increasing, we have to have a min. Make sense? Now comparing what we've got on the interval -infinity to 0, we found we were decreasing. On the interval 0 to 3 over 4, again, begin decreasing, and on the interval 3/4 to infinity, we're increasing. Right? So all the same idea here. Something I should point out. If you notice, I happen to choose the same test points they did. It's just because it was a nice, normal, random number to pull, right? Like, if you can choose whole value integers, go for it. If you can get those integers out, use them. If you can get nice rational numbers, use them. If you can get 0, always use it. And I just wanted to point that out really quick. So as another example, let's consider we've got the function 2x minus 3x raised to the 2/3 power. When we take the derivative of that, it turns into something nasty. But notice this thing can have a 0 in the numerator. And in theory, if x could be 0, we'd have a discontinuity, right? Like we would get nothing out of that. So we have two different critical numbers. We have when x is equal to 1 and when x is equal to 0. When x is equal to 0, it's going to be some sort of a discontinuity, right? That's what's happening up here. When x is equal to 1, that's what's happening down here. Now notice what we're saying isn't that this thing, this derivative, can take on x equal to 0. We're just saying that it's a critical number. Our function can take on x is equal to 0, but our derivative cannot. And that's why it's a critical number. Does that make sense to everybody?
Yep.
Yeah, awesome. So having said that, there's another concept of absolute min and absolute max. Since relative min and relative max are going to be points along these troughs or peaks, what do you think an absolute min or an absolute max would be? Folks at home.
Is it where the whole function stops at that point?
If y'all are saying anything, I can't hear y'all.
Is it where the function like stops?
Not quite where it stops. It's just going to be the largest possible value of your function in an interval. Having said that, we are going to have to check the endpoints of our interval. So an absolute extrema is going to be the most extreme value, small or large, that our function can take on. So for example, we've got an absolute max at the end of our interval. But we have an absolute min at one of our relative minimums. So what a relative minimum is a point where if you jiggle your x values, anything around that point is either going to be larger in the case of a minimum or smaller in the case of a maximum. In the case of an absolute max, any value in that interval, your function will always be smaller than the max. Conversely, if you have an absolute min, for any value in that interval, your function will be greater than. Make sense? I'm assuming by the silence that's a yes.
Yeah.
Awesome. So, jumping then to the extreme value theorem, if a function is continuous inside of an interval, we're always going to have some extreme absolute min or absolute max. Now, looking at that, you may ask, well, what about a constant function? What about something like g of x is equal to 1? And we can graph it. According to this extreme value theorem, every point is an extreme max and min. Does that make sense to everybody?
Yeah.
Yeah, cool. So as another example, let's say we've got h of x is equal to 9 minus x squared. And this is on the interval -3 to 3. Then we're going to have a relative max as an absolute max here, right? We're also going to have two absolute mins. But no relative min. So an absolute max and an absolute min are the absolute largest numbers that our function can be, or the absolute smallest numbers that our function can be on our given interval. But the relative values have to be peaks or troughs. Make sense?
So if there's multiple, like there is down there, can it not be the relative minimum?
No. In this case, these will just be absolute mins. So the difference between an absolute max, or I mean an ab extremum or a relative extremum, would be something like this. Here we have a relative max, a relative min. We also have, put my endpoints here. We also have an absolute max and an absolute min, right? Because this point is lower than every other point on our graph. So this thing is also an absolute min. Having said that, how do we check for these things? Well, we're going to use the derivative test for max and mins again, but we're also going to include checking our endpoints. So we're going to look for relative maxes and relative mins, but we're also going to compare those against our extreme points, our endpoints. Does that make sense?
Yeah. Yeah, that makes sense.
Why? Why
Yeah,
is it
that
that we would only check these points? Well, let's consider a relative max. If we have a function with a relative max, it's going to be on this interval let's say this thing is going to have a relative max over here. It looks something like this. It's up here. Now we know moving to the left, to the right, we're going to have to decrease at least for a little while, right? So let's say moving to the left, we decrease. Now moving to the right, we're going to decrease for a little while. So the only way for this point, for this end point over here on the interval to be greater than this absolute or this relative max is if we have a relative min somewhere. And we turn around, we start moving up. So the only way for our function to have an absolute max or an absolute min is for it to end up at one of these extreme points, one of these relative extreme points, right? Or for it to end up at the boundaries. Does that make sense what I mean?
Yep.
Yep, awesome, cool. So we're given then in this first example, the function x squared minus 6x plus 2 on the interval 0 to 5. Well, the derivative of this thing, oh, I forgot the interval. x is in the interval 0 to 5. So the derivative of this thing, f prime of x, is going to be 2x minus 6 and this is only going to be 0 whenever x is equal to 3, right? So now what we want to do is check if this point is going to be a relative min or max, because this is our only critical number, and if either of these points are, right? Having said that, we know something about this function. The graph of this function is going to look something like this, right? Just because it's a parabola and x squared is positive. So we know it's going to look something like an upward facing parabola. So having said that, we know just from that little bit of knowledge that this x equal to 3 has to be a min. Does everybody follow that logic?
No.
All right, so let's see why. There is no nice way to factor that. That's 0, that's 2, this is going to be over at 3. So the graph of our function is going to look something like this. And we know it's going to look something like this because it's a polynomial. Its highest power is 2. And there's a positive term on that 2, right? Since x squared, since that term is positive, we know it's going to be a parabola shaped like this. And since we know that x equal to 3 is a critical point, we know that that has to be where a parabola flattens out. So it's got to be the min here, right? So just as one example of how we can skip a step, if we know something about the function itself, we could do something like this and say, all right, well, I know this has to be a min. Now I have to check what our function is at 0 and what it is at 5. Otherwise, I'm going to have to check all 3 points. And that's all I'm trying to say here. So having said that, let's check our function now. At x is equal to 0, 3, and 5. At x is equal to 0, implies we have 0 squared minus 6 6 times 0 plus 2. This thing's going to come out to be just 2, right? Now, at x equal to 3, we've got 3 squared minus 6 times 3 plus 2. So this is going to come out to be 9 minus 18.
-7.
-7?
Yeah.
It's going to come out to be -7 is equal to f at 3 and now x is equal to 5. We're going to get 5 squared minus 6 times 5 plus 2. It's going to be 25 minus 30. So that's going to be -5 plus 2. It's going to be -3. So what we know from this then is that our absolute min occurs at 3, right? Because -7 is less than -3. And certainly less than 2. And we know that our absolute max has to occur at x is equal to 0. So to see all of this side by side in practice, we check our 2 endpoints, 0 and 5, and we check our 1 critical number. At endpoint 0, we get 2. At our critical number, we get -7. And at our endpoint 5, we get -3. Two is the maximum of all of these values. -7 is the minimum. So x must be an absolute max. X equal to 0 must be an absolute max. And x equal to 3 must be an absolute min. Check it out. It's also a relative min. Does this make sense? I'm assuming by the silence that's a yes. So having said that, what time is it? 6 minutes. I'm going to give y'all 2 minutes to work on this problem. For those of y'all at home, this is slide 38, if you can't see it on the projector. I'm going to give y'all like 2 minutes to work on this. So what did we come up with? Folks at home, what do we think the absolute max of this profit function is? Well, we're going to have to check the critical number, 24,400, right? And we're also going to have to check at 0 and 50,000, which of those values is the greatest, right? Yeah? I'm going to go ahead and tell you that it's 24,400. But I know what the graph of this function looks like, so I cheated a little bit. Given that our function's a parabola, and it's an inverted parabola, we knew that that critical number was going to be it. That's how I was able to figure it out really quick. But using the process, we go through and we say, all right, what's our profit function? What's the derivative of that? Let's find our critical number. Now, let's go through and find out what our function is at our first endpoint, at each of our critical numbers, and then at our last endpoint. That's exactly what they've done here. Having said that, they also skipped this step of actually checking these other endpoints because they knew what the geometry of this graph was going to look like. They knew what that curve was. So they were able to skip testing the other values. But we would go through this method, check all three values, and then determine which one's the absolute max in the case of this problem. Does that make sense to everybody? Having said that, I will let everybody go. Have a good one, everyone. You'll have
Thank you so
any
much.
questions around for a little bit.